We're going to mix this water and this water together to see what happens during that mixing. Okay, so the way we do that is very simple. We're going to add a mixer object, and then we're going to bring them together. So what I want you to do is, again, if we have to go to a higher level in order to see information in the action panel. And in order to do that, you either have to be at the stream level or the stream object level or the default stream level. I like going to the default stream level because it reinforces the purpose of this. Okay. Then I'm going to add a mixer. Good. So we're just going to call this mixing waters. Nothing special. And then we're going to bring those two reconciled waters into this mixer. There are three ways to do this. You can either, in the mixing water object, you'll see that there's the available stream and selected stream. You can either just highlight both of them and bring them in with the arrows. You can double click them in. Or what I think is cool, you can single click on the stream in the navigator panel and drag it into the selected. Sometimes that's easier because you know where it is here, but you have a hard time finding it there. Now, the mixer object is pretty cool. The mixer object, it has a lot of feature functions. First of all, when you use the mixer, you have the ability to set the output temperature and pressure in that mixer. So the mixer doesn't just have to be an adiabatic mixer. It could actually be a mixing unit with a heat exchanger with a controller, for example. Or it could be a mixing unit with a pump in order to raise the pressure and a valve, right? When you bring things together by default in a mixer, the default setting is going to be single point mix. A plus B mixes together to create the output. Now, in terms of what A plus B contains, I want you to notice the grid entries here. There is a top level row called multiplier. Now, I want to get to that in just a second. What I want to do first is look at the third row, total inflow. Total inflow right now is set to 1 liter for each. It's set to 1 liter for each because that's what the stream that you brought in is set to. So this value here, this 1 liter, and this value here, this 1 liter, is essentially what these two values are. 1 liter and 1 liter. Same with the temperature and pressure. The software pulls the inflows, the temperature and pressure of the stream into this mixer. So we know what the starting volumes are and the starting conditions are. Therefore, when we mix them together, we can see the starting conditions and the final conditions of the case. That's the difference between a mixer and everything else we've done. Everything else we've done to date, we've only, whether it's a single point or a survey, is that we only calculate the final state of the system. We don't know what the starting conditions were. We just say this is the final state of the system. So when we did a pH survey with CO2, we're saying that at this pH, we calculated the state at 6.6 pH with this much CO2 and this much sodium hydroxide. Mixing waters is different. Each of these streams brings in its own enthalpy, right? Its own mass. And then when we combine them, it creates the combined mass and the combined enthalpy. And then that shows up, the energy shows up depending on how we do our calculation. So let me stop talking and just press the calculate button. What I want to show you is how the software thinks about material balance and total energy. Right now, what the software is doing is it's generating the chemistry models for both streams, combining it into a single chemistry model, and then running the calculation. What the software computes is that, again, since we set the temperature to 25 degrees Celsius, and even though both streams came in at 25 C, there was a certain amount of heat that had to be added to the system to keep that temperature where it was. Because by mixing them together, it was slightly endothermic. Okay? The temperature would in fact drop slightly when we brought these things together. It also calculates that when we bring these two streams together, that you're going to form two phases, a water phase and, again, a solid phase of unknown. We don't know what those are yet, those solids. It also shows you what the mixture pH is, and plus whatever else. So again, typical mixer set to isothermal.
Hey, Jay.
Yeah.
Is there the option available to see when we mix two stream what we get base case without having the software forcing it back to an isotherm of 25 C?
Yeah. Now let's do the second calculation. Everyone do this together with me. Change it from isothermal to adiabatic. Now we close the system off to any energy transfer. Recalculate. This will be faster because it doesn't have to regenerate the model. It should be faster, maybe not. And now you're going to see that we're going to add 0 joules of energy, and we're going to see what the final temperature is going to be. Now it's just working like a normal adiabatic flash tank. Taking that further, what we then can do is not just look at the energy balance, but look at the mass balance. If, for example, we wanted to go from 100% of the high calcium barium brine to the high carbonate sulfate brine. So what I want to do now is just describe the different types of calculations available. The first two are obvious, right? I want to adjust temperature and pressure, kind of like doing a temperature and pressure survey. And so in this case, I'm mixing both at 50-50, 1 liter of each, but then changing the temperature. I'm not interested in that survey right now. Likewise with the pressure survey, I can mix two streams together, but I can vary the pressure. What happens when I do that? Not interested. The third option, volume, is when I can take one stream, fix its volume, take another stream, and adjust its volume. So let's say I wanted to use 1 liter of water of high calcium, but then I wanted to go from 0 to 10 liters of the high carb sulfate brine. Then I'd use the volume survey. The ratio is if I want to go from 100% of one to 100% of another. That's what we're going to do next. And lastly, the multiplier is when I utilize this top row here. Right now, this multiplier is essentially saying, if I want to use, if this value is set to 1, then I'm adding 1 liter of this brine. But if I set this to 5, then I'm going to multiply this volume by 5, and I'm going to have 5 liters coming in. And maybe I want to do 5 to 3. Right now I've got 8 liters total, 5 of this and 3 of that. What the multiplier does in the mixing is I take one of these multipliers and I vary it. Now in this case, what we're going to do is we're going to use the ratio. Okay. First of all, we're going to set both back to 1. Not that it matters, but let's just set both back to 1. Okay, just till we get back to our default settings. Right now, our calculation is adiabatic. So in fact, you can see that the temperature value is green, meaning that that's just an initial guess. But the button is red because I have to tell the software what is going to be my independent variable. What am I adjusting relative to the other? So I do have to go into specs. And in this case, I'm going to adjust, which one? Bear with me here. I'm going to adjust the high calcium barium brine. So when I do my survey, my independent variable, well, it's actually going from 0 to 100%, but it's going to go from 0 to 100% of the calcium barium brine. Okay, or 0 to 1. So what we're going to do is we select the high calcium barium reconcile. That's the one that we're going to use as the adjustable parameter. Right? And then this one will be adjusted relative to this. But this is the one that you're going to see on the plot. And then in the survey range, again, you'll start with the 0 amount of the calcium barium. You'll work your way up to a mole fraction of 1. But in this case, rather than go in 10% intervals, let's go by something a little bit more detailed, like maybe 5% intervals. So do 0.05. Okay. Or, better I show this now, you can go by point list. I can actually add, 0, 0.1, 0.2, 0.25, 0.4, 0.5, etc. Okay, that's another way we can go. But in this way, we're just going to go linear, 0 to 1, which means 0% of the calcium barium to 100% of calcium barium in 0.05 here. Okay, in 0.05 increments. Press OK. The light is green. Press calculate. And as it's calculating, what I'm going to have you do is go to the plot. And once it starts generating a plot, what we're going to do is we're going to plot the solids that are forming. So right now it's plotting. I can go into variables while it's plotting. I'm going to remove the dominant liquid. And I'm going to go into solids. And this time I am going to use that dominant solid option. So while it's doing its calculation, I can edit the plot however I want. In this case, I'm going to use the dominant solids as my feature, as my variable. And the three important solids, the only three, are the calcite, the barite, and the strontium sulfate. And what this shows is, again, notice the x-axis is the high calcium barium reconcile. That is the one that we selected in the specs window. That's why we needed to select it. We had to show something that'll appear. And then depending upon the ratio, the volume or molar or volume or mass ratio, it's all the same in this case, of the two, I can see that I'm forming actually different solids. Okay, so here, for example, when it's 30% by volume of high calcium barium, I get the highest concentration of calcite that precipitates. But if I go to 95% of the high calcium barium brine, I get the highest concentration of my barite scale. So again, the actual numbers are not important, but knowing how to do your survey is. Okay. And by the way, I misspoke a second ago. I said that volume, moles, and mass are the same. They're not. We are adjusting by volume here. So it's, and remember, the densities are different. So, and the moles are different. So the moles and mass will be slightly off. So these are specific to the volume, this ratio that I'm doing. If I had chosen mass as my inflows, right, instead of concentration, then it would have been, the ratio would have been specific to the mass of each.
And that will change the dominant species?
No, it'll be the same. It's just that when you mix things together, for example, I misspoke and I wanted to correct that misspeak in that case. But that is, again, a very simple example of how you use the mixing water. And just to take it one step further, let's click on variables, remove the dominant solids, and let's take a look in the stream parameters what the final temperature is. So open up the variables again, remove the dominant solids from the Y1 axis, and then expand the category called stream parameters. In there, you're going to find the pressure, the stream amount, and the temperature. Put the temperature in there. Let's see how the temperature wiggles around as you either precipitate or dissolve things, or as you mix things together. Okay. It's not much of a difference really, but really what happens is as you form your calcite solid, it's slightly endothermic, so you have essentially a slight drop in your temperature, but nothing really significant here. All right, I'm going to stop there, and because I threw a lot at you in the last half hour in terms of all these little feature functions with the grinding out water analysis and then the mixer. But I didn't really cover everything that these tools can do. So I want to stop and ask, which one of these tools, right, whether it's a single point calculation, the survey, the water analysis, or the mixer, do you see yourself using the most? And which ones do we want to, we have 15 minutes left, which ones do we want to focus on next? Which one do you feel least comfortable with, for example, that you think you need to know more?
I'll go first, AJ. From my perspective, number one will be set point, and number two will be the mixer. Number three will be water analysis.
Okay, you said set point. Can you explain that a little bit more?
I'm sorry, I misspoke. What I meant is the set.
You mean like in a single point calculation, you set?
Yeah, sorry. Yeah, I was at loss of word. Thank you, AJ. I was reading something else here. Single point. I apologize.
Okay.
I'm sorry. I was reading about a thermal well, and I said a set point. I apologize.
That's okay.
Okay. It's okay. Single point.
Single
Thank you,
point.
sir.
Yeah. So again, it was single point. What was the second one again?
The mixer.
Mixer is second. Okay.
Okay.
And how about the others? Brett, Marina, Faisal, which ones do you, I'm trying to find commonality. Faisal,
water analysis. Water analysis.
Water analysis. Okay. Marina, how about yourself?
No, for my side, everything is okay. I wanted to know what if you don't mix two liquid phases. If you mix, as I mentioned before, a gas phase with a liquid phase.
Oh, that's right. You did mention that. Yeah. Okay. How about you, Brett? Which one?
My preference, I'd really like to see some of the analysis of with corrosion using the redox. That'd be my main purpose.
Ah, yeah. You know what? I think what we have to do, Brett, you win the gold cup there, because the redox is part of the thermodynamics, which is part of our this calculation, this course, the full course here. Even though redox takes a part in corrosion, it's really the basis is here. So we're going to spend what time we have right now going over redox, and then if we have time, we'll try and do the other things. Okay. So what that means is this: we're going to I saved the case file, and what we're going to do is we're going to do a couple of redox calculations just so you can see what's happening in them. First things first. Let's create a new stream. Okay. Top level stream, add a stream. And we're going to do something very simple to get started, but then hopefully it'll become more clear as we do it. We're going to call this calculation iron oxidation. Okay. And then what you're going to do in the grid, again, we're always working in the grid, and we haven't played around with the units. We don't want to do it here either, because this is moles are a great way to understand redox. It's not the perfect way. The perfect way is to use oxidation states, right? How many electrons can be given or taken away? But we're going to have to live with this. Type in Fe. When you type in Fe, essentially you're adding elemental iron to the system. And then add O2 below it, right? Now, just for those of you not entirely familiar, iron can give up either 2 electrons or 3 electrons. Okay, oxygen in the molecular state each atom will accept 2 electrons. So oxygen can accept a total of 4 electrons. Iron can donate either 2 or 3, depending upon the final state of the system. Okay. Now, by itself, if we were simply just to do it as is, add a single point calculation, for example, and press calculate, what we're going to see, actually, I did it the wrong way, but stay there. If we were to add iron and oxygen, again, no, we don't add any material yet, right? And we just press the calculate button, or even looked at the chemistry. In fact, I want to restate this. I want to go back to the stream level, and I want, forget about the single point, and go to the report. In the report, there's something called a speciation summary. It describes what species are being considered in this reaction, or in this stream. By not having redox on, I have elemental iron only, and I have molecular oxygen only. There's no indication that iron will oxidize to iron 2 or iron 3. But if I were to click on this button right here, RE, you see what happens, the toggle. All of a sudden, the iron redox chemistry is now incorporated into my stream. And I have all these different oxidation states and species that's going to be included. Specifically, I've got iron 2, or there's iron 2 and iron 3 present. From the oxygen side, it's really from the water side, I also now have hydrogen present, right? Because that's going to be that's the splitting, that's the hydrolysis of water. Water can form hydrogen and oxygen when it splits. So redox has an important step of essentially turning on and off certain oxidation states. Going further with that, if I were to click on chemistry and then model options, and then I go to redox, and then I expand each one of these sections in redox, you can see that there's little pluses, there's little check marks for each essentially oxidation state. If I chose to, I could tell the software that, yes, I want to include ozone, or no, don't include ozone, or if I'm going to oxidize iron, only let it oxidize to iron +2. Okay. Meaning that it's not allowed to fully oxidize to iron +3. Anyway, so we're going to keep everything on. We're going to press OK. Yeah.
Sorry, but I can't see in the report the speciation summary.
You can't see the speed. Okay. Go back. Go to the stream. Are you at the stream level? I made a mistake by adding a calculation. Click on the stream itself. And go to the report. Do you see the speciation summary there?
No, yes. Thank you.
Okay. Yeah. I misspoke. I wanted to do the calculation first, but I realized it's better to show what's being calculated. Okay. So now that we've done that, and now you can see what's being studied. Now we can go to the single point calculation. Okay. And at this point, what we're going to do is we're going to add a little bit of iron. Let's say we add 1 mole of iron, but no oxygen. Okay. You press the calculate button. And what's going to happen is iron, again, it's got 2 electrons to donate. The only thing now present that'll accept the electrons is the hydrogen ion, right? There's no oxygen present, and the oxygen in the water is already at its reduced state. So the only thing that'll take electrons from the iron is going to be the hydrogen ion, which means that we're going to produce hydrogen gas. So once we've done that, press the calculate button. And what you're going to see, if you look on the right-hand side, is you created essentially 3 phases. pH is about 9. Okay. And what we're going to see is that we split water. So go to the report, scroll down to the speciation table, the species output. What you're going to see there is that water, which was originally at 55 moles, remember that? It's now at 54 moles because essentially I lost 1.3 moles of it to form hydrogen gas. Likewise, the iron oxidized to both iron 2 and a little bit to iron 3 to form a magnetite film at this pH, or a magnetite at this pH. So this chemical reaction, where elemental iron reacts with water, iron splits water to form iron plus 2 and iron plus 3 and hydrogen gas, and the iron plus 2 and iron plus 3 then react with the available oxygen from the water to form that magnetite film. Everything else is very low in concentration.
And this is, AJ, assuming the water has 0 dissolved oxygen in it.
Precisely. And we're going to flip that around in just a second. And to make that point, look at the oxidation reduction potential, minus 0.5 volts, right? A negative number, depending upon where you are in the pH, negative number, think, okay, it's going to be a reducing environment. It's not always true because it really depends on your pH. But in this case, you can say, okay, yeah, negative, I've got a reducing environment. Now let's go to definition, back to the definition, and add, let's not add a lot of oxygen. Let's add maybe 0.5 moles of oxygen. Not too much, too much. Add 0.1 moles of oxygen. Okay. Again, we're not talking about like 20 ppb or 8 ppm or anything. We're just doing things stoichiometrically right now. And then recalculate. And then now look at the report. Now you're going to see things a little bit different, not a whole lot, just a little bit different. Right? We need less, we're producing less hydrogen now because oxygen, molecular oxygen is there to accept some of those electrons. So instead of using 1.3 moles of hydrogen, producing 1.3 moles of hydrogen, we produce 1.1 mole of hydrogen. There still isn't any free oxygen remaining because we still have a reducing environment. But we should probably see this number have gone up a little bit. I think we were at minus 0.56 volts. Now we're at minus 0.52, right? So we've shifted the equilibrium a little bit because we added a little bit of oxygen. Now let's take the same idea, turn it into a survey, and add oxygen using a composition survey. So again, I'm kind of speeding this up a little bit because we only have 4 minutes left. But let's click back on the stream. Okay, now at the stream, you're going to add a survey calculation. You're going to start with 1 mole of iron. And again, remember, 1 mole of iron will give up 3 electrons. Okay. 1 mole of oxygen will accept 4 electrons. So you only need about like 0.8 or 0.75 moles of oxygen to fully oxidize iron. The reason I'm telling you that is because let's now do a composition survey. Let's add oxygen in log scale. Let's do it from 0 to maybe 0.8 moles. So change this to composition, go to specs. We're going to select oxygen as the adjustable parameter. Go to survey range. Let's change this to log scale. Now in log scale, the start has to be a positive value, can't be 0. So let's put in 1e to the minus 6, some small number. And let's end at 0.8. And let's go with by 20 steps. What the heck? Electrons are cheap. Now we're working in log scale, so we're going to be looking at essentially 6 orders of magnitude in terms of oxygen concentration. But we're only using 20 points to get there. So there's some areas will still be sparse. Press OK. Now press calculate. It's real quick. And we're going to look at a couple of things before we have to quit. Go to your plot. First of all, we see what happens when we're no longer needing to split water, right? When you split water, you make hydroxides. Now we don't need to split water anymore. We have enough oxygen. So all of a sudden the pH drops. That's kind of cool. Okay. But let's do something else. Let's go to your variables. Let's remove pH. and go to your thermodynamic properties. No, I'm sorry, wrong. Go to your additional stream properties and find your redox ORP and put that on the Y1 axis. And then while you're in here, go to your vapor and add hydrogen to the Y2 axis and oxygen to the Y2 axis. Okay, so additional stream parameters is where you're going to find your ORP. Put that on the Y1 axis. And then go to your vapor section and add oxygen and hydrogen to the Y2 axis. And then the last thing you're going to do, and we're at the top of the hour, is on the x-axis, turn this into log scale. So what we can see is that here's the ORP. It pretty much stays constant at minus 0.5 volts until we have excess oxygen. Then it just shoots up. But as we add oxygen to the system, we see a more gentle slope dropping because we need less hydrogen gas. We're making less hydrogen gas because instead of hydrogen accepting the electrons, hydrogen ions accepting the electrons, the oxygen is. So eventually it drops. Now we may say that we use too much of a dynamic scale here. In fact, maybe we would have been better at a linear scale rather than a log scale. In that case, you just go back to definition, go back to specs, go to survey range, change it to linear, make this 0, use however many points you want, and recalculate. And now you just start interpreting. Take this off of log scale, and now you see essentially a different type of plot. What's cool here, though, look at this. You have essentially a stepwise. Iron, all right, this is iron plus, this is hydrogen gas present here. Hydrogen gas, I think this is when iron plus 2 is present. Excess oxygen here. So essentially you have 3 levels of redox potentials simply because you're at different points in the amount of free oxygen present. Anyway, we're past the top of the hour. I'm so sorry to keep you. Hopefully this helped out a little bit. And Brett, thanks for reminding me that we had to get this done. Okay, I didn't give you as much as we should have, but I'll send you part of chapter 6 for anyone interested in this. And actually it's in chapter 2 and chapter 6. So you can learn about this more. And then if you guys are taking the corrosion class, then we'll study this in a lot more detail.
And AJ, if you can also send some literature on this as it pertains to scale formation, the FA3 plus contribution to scale, the FA2 plus contribution to scale, which one of them is more stable versus the other. So that would be...
The only thing we're going to have on that is a general corrosion paper that we wrote back in 2001. It talks about essentially how we model the protective and passive films, but we don't necessarily get involved with the integrity of the film. That's outside of our skill set. And we know about it, but that's not what we try and calculate. It's just because that gets into the dynamics of it.
No, certainly. And an iron oxide scale generally on carbon steel is not going to be, it's a quote unquote flaky scale. It's not like a sulfide scale or anything. It would be good to have your paper to see the different contributing factor in the formation of those 2 type of scales. Okay, good. Yeah, so everybody, you'll get this as you finish up. You'll get this case file. I'll send you chapter 6, which talks about redox chemistry and Porbet diagrams with that. And then also I'll send you, for those interested, our general corrosion paper that just describes how essentially we do corrosion calculations of redox chemistry. And then with that, how we calculate the formation of films. Thank you, sir.
Great. Guys, this was a lot of fun. I realized, oh, Brett, you had a question. Go ahead. Mm-hmm.
Can you send us the training details of that general corrosion training?
Yeah, sure. It's not my area. I'm trying to think who would be the best person to get it for you. But what I'll do is I'll pass it on to Jim. Jim's my colleague. We run what's called the application engineering team together. but he focuses on the training and support. So I'll just pass it on to him to see how that information can be sent to you, because we're still not sure if that should be sent from the sales team or from us. So one way or another you'll get it.
And one more thing, AJ, when Jin Jiang reconcile all those species, and remember we discussed earlier, put it under the parent, for example, CO2, as opposed to going down and hunt down for all the CO2 resulting type species. When you do that reconciliation, would we receive a notification with that update, or how does that work?
Yeah, so what happens is because those things happen at release time. So right now we've got version 11.5, version 12 will be released, let's say in December. If that feature function request makes that release, then every client gets a link that shows what improvements were made in the software.
Perfect.
And so you'll get, they could be a couple hundred in some cases. But if you actually if you submitted it directly, then you'd actually get a request. But I think this one, since it's so important, since it's such a good one, I think I'm going to do it under a general release so everybody gets to know about it.
You are truly a gentleman, Mr. Gurbino.
Thanks. Hey, thanks everybody. If you have any questions, again, you can always email us. There's a lot of ways of us helping you all out. So, okay.
Thank you.
Okay, thank you.